try that. Okay, so let's just go through it. It's chapters 17, 18, and then also this little section, chapter S3, which is general relativity. So we talked a little bit about star formation for the last exam, but just know the basics of star formation, that stars form from nebulae. They collapse under gravity, and when they're collapsing and forming, they're called protostars. And then what event marks the official birth of a star? That's when hydrogen fusion takes place in the core. So before hydrogen fusion takes place, it's a protostar. After it takes place, it's a main sequence, just a normal star. And then you guys know, what is the importance of mass for a star's life? Mass determines everything. It's how fast stars form, it's how quickly they live their lives, how hot they burn, and what they eventually become. So mass determines everything about a star's life. All stars go through a similar sequence of phases in the beginning. So they begin as protostars, then turn into main sequence stars. Then once they run out of hydrogen, they begin helium fusion and become red giants. After that, it determines its phase. Yeah. So for massive stars, it becomes a supernova. And after that, it becomes either a neutron star or black hole. But for stars like the sun, there's no supernova because it doesn't have enough mass. The core collapses, it becomes a white dwarf, and throws off the outer layers as a planetary nebula. So the sun, in another 5 billion years, will become a white dwarf and planetary nebula. More massive stars end as supernovae and then become neutron stars or black holes, depending on how much mass is left over afterwards. So just know the sequence of stages for the different size stars. And then this question here, how does mass affect a star's luminosity, core temperature, lifetime? Once again, more massive stars shine brighter, they have hotter core temperatures, and they have shorter lifetimes. So the bigger the star, the quicker it burns through its fuel, and the shorter the lifetime. And then once again, know the HR diagram, where different mass stars are. So on the HR diagram, there's a line for the main sequence, which goes from the lower right to the upper left. High mass stars are in the upper left part of that line. Medium mass stars are kind of in the middle, and the low mass stars are in the lower right part of that line. Okay, so everything about a star's characteristics depends on mass. And then this last thing, formation of elements in stars, nucleosynthesis, it just means that new elements are produced in stars. So stars fuse hydrogen to create helium, then they fuse helium to create carbon, carbon to oxygen, oxygen to neon, and so on, all the way up to iron. And then stars can't fuse iron. The iron atom is too tightly compacted to be available for fusion, so then the core collapses. Once the core collapses, then you get runaway supernova event, and that creates all kinds of heavy elements beyond iron. So gold, silver, iron, uranium, those are all created in supernova explosions. So nucleosynthesis just means the formation of elements in stars. All the elements that we see in our lives come from stars, which is actually pretty cool.
Yeah.
Yeah. So the end of a star's life takes us into the death of stars, which is chapter 18. So 3 different final states for stars. You can have white dwarfs, and then if it's heavier than a white dwarf, it becomes a neutron star. Even heavier becomes a black hole. And to put specific numbers on it, stars which have a mass less than 1.4 times the mass of the sun becomes white dwarfs. If they have a mass 1.4 to 3 times the mass of the sun, they become a neutron star. 3 times or greater, it becomes a black hole. So there's precise numbers for these different stages. Now, white dwarfs are really interesting because that's something the size of the sun packed into the area the size of the Earth. So it's incredibly small, it's incredibly dense, and it's not burning because of fusion, it's burning because it just has leftover heat from the core's life. So it continues burning until it cools off and eventually becomes a black dwarf. Neutron stars are even smaller. So you take something the size of the sun, squeeze it down to the area of Boston or so, right? So roughly 10 miles across, and that's a neutron star. So they're incredibly dense, and they spin very fast. So as a star collapses, it begins to spin faster. So neutron stars spin something like 30 to hundreds or even thousands of times a second. So they spin very fast, they have very strong magnetic fields, and they send out pulses of radiation, like radio waves or light waves, or visible light. And when that beam of radiation crosses our line of sight, we see a flash of light. So it's called the lighthouse model. So it's like a lighthouse spinning in space, where we see flashes of light, and that's called a pulsar. Pulsar is just a rotating neutron star that emits radio waves. Now, if you have even more mass, then something the size of the sun gets squeezed down even smaller, down to the size of roughly 3 kilometers, and that's a black hole. Black holes are so dense and their gravity is so strong that not even light can escape from them, which is why they're black. They have a radius, which is called the Schwarzschild radius, which determines the event horizon. The size of black holes depends on mass. More massive black holes are larger, and they have a larger Schwarzschild radius. And the edge of a black hole is called the event horizon. Once you go into the event horizon, you can't come out again because the escape velocity is greater than the speed of light. So you can go into a black hole, but you can never come out because you'd have to travel faster than the speed of light, and nothing can go faster than the speed of light. So even light gets trapped in a black hole and can't get out. Now the singularity is the point of mass at the center of the black hole. So take all the mass of the black hole, squeeze into a single point, and that's what the singularity is. And so it's thought to have infinite density. So we have no idea what that means, what's infinite density like, but it's where all the mass of the black hole is concentrated. And then once again, larger black holes are more massive. So black holes can be any size. They can be the size of atoms, they can be the size of the solar system. It all depends on mass. And we think there could be millions of black holes flying around our galaxy. They're really hard to detect, but they're out there. Okay. And Einstein's general theory of relativity predicts that black holes should exist. So Einstein says that what gravity is not a force, but it's the curvature of the fabric of space-time. So he says space and time aren't separate, but they're woven together into a fabric, and anything with mass is going to create a dimple or a curve in space-time, and light rays follow that curve in space-time. So near a massive object like a star or a neutron star or a black hole, light rays will actually bend in the presence of that curved space-time. Other effects are that in a strong gravity field, time slows down, so clocks run slower in a strong gravity field. Space is bent, so light curves, and space, time, and light are all interrelated in Einstein's theory of general relativity. So his theory predicts that black holes exist, that this is an area of space-time where space is infinitely curved upon itself, and that's what we call a black hole. So pretty amazing stuff. Mm-hmm. One other thing I want to touch upon is how do we actually know that black holes exist? Can we actually detect them? Well, there's 3 ways we can detect them. So one, oftentimes black holes are in binary systems with other stars. And if a star is orbiting a black hole, the black hole will sometimes draw off matter from the star. The matter will swirl around and go into the black hole. And as it goes into the black hole, it creates what's called an accretion disk. And that accretion disk heats up because of friction and sends out light because it's at a high temperature, usually X-rays. So oftentimes what people will see are X-ray sources in a binary system. They know that the star that they can see isn't emitting X-rays, so there must be a black hole that's emitting X-rays. So that's a giveaway. And the first black hole discovered, Cygnus X1, was discovered that way. There's an X-ray source in that area. All they saw there was a blue star, so they knew there was a black hole there. The other way that people detect them is by their effects on things around them. So for example, in a binary system, this star will appear to be going around nothing. So they know the black hole's there because they can see the star moving. They can see the black hole's gravitational effects on the star. So even though they can't see the black hole itself, they can see the effects of the black hole on the stars nearby. That's actually how they found the black hole at the center of the galaxy, was they watched the stars near the center of our galaxy. They saw they were moving in really weird ways, They calculated the mass that would cause that effect, and they found that there's something there with something like 2-3 million times the mass of the sun, causing the stars to orbit really weird. So at the center of our galaxy is a supermassive black hole, and they can even measure the mass. Now, the third way to find black holes is if you watch the night sky, occasionally a black hole will be moving in between the stars and will bend light around itself. So they'll look for these little, what are called microlensing events, where they see a little flash of light or they see light being bent by something that they can't see. They can determine what's causing that curvature and find out it's a black hole. So even though we can't see black holes directly, we can see their effects, and that leads astronomers to have pretty good confidence that black holes exist and actually measure their properties, such as their mass, how big they are, and velocity and stuff like that. So pretty amazing stuff.
That's pretty good.
Yeah.